chromatographic techniques have been developed taking gas chromatography as the model. So, in this unit, we'll have some recapitulation of basic aspects. It is column efficiency, solvent efficiency, instrumentation, the mobile phase, that is the carrier gas, then columns, stationary phase, the support and liquid phases, then sampling, then applications. So these are the objective of today's class, which deals with mainly gas chromatography. So today we'll discuss both the gas chromatography and also the HPLC, the high performance liquid chromatography. So the recapitulation of basic aspects, these things already you know in a chromatogram what we deal with. In the operation of a gas chromatograph, the solutes in a mixture are completely vaporized in the injection port and they are moved through the column by a carrier gas under pressure. It is in the column where separation takes place. From the column, the separated solutes passes through a detector where they are sensed, generating an electronic signal. The signal is then amplified and normally displayed on a strip chart strip chart recorder. The trace plotted on the recorder is called the chromatogram. It is a plot of the detector response in millivolts as a function of time. So usually the chromatogram looks like this, where we are getting the solvent peak as a very having very high intensity, then different components. So from solvent to component peak, this is known as the retention time. So under a given set of experimental conditions, each peak has a characteristic retention time and the retention volume VR that are useful in qualitative analysis of the solutes. The retention time for solute A is depicted in the figure as the distance from the point of injection to the maxima at A. So from here to here, this is the injection point, then this one. Similarly, that for B it will be TRB and for C it is TRC, like this. So retention time. So VR by definition, VR will be equal to TR plus TR into FC, where VR is the retention volume and FC is a constant. If the flow rate of the carrier gas is constant, then we can get VR equal to TR into FC. FC is the flow rate. Okay. In practice, one can use either retention time or retention volume for qualitative analysis. Retention time. So in GC, this behavior is often shown by air or methane, and the peak is often called the air peak. The symbol VM, sometimes called the hold of volume or void volume, serves to measure the interstitial or interparticle volume of the column. The term dead volume, while not recommended, is also widely used. So Tr prime equal to Tr minus T naught, where Tr is the adjusted retention time and T naught is the retention time for air peak. Thus Tr A, Tr and B, Tr, C, they are are the adjusted retention times for solute A, B, C respectively. Similarly, for retention volume, Vr prime will be equal to Vr minus Vm. So Vr is the adjusted retention volume and Vm is the hold off volume, and Vr A, Vr B, all these things are the adjusted retention volume for solute A, B, C respectively. Then the area under the curve. The detector response or area under the curve is proportional to the quantity of material passing through the column. So therefore, a quantitative measurement can be made, and for this purpose, a calibration graph of area under the curve versus quantity of solute injected need to be constructed, and for each solute separately. Okay, so if we refer the first figure, this one, it is based on area under the curve of solute. B is present in the large amount, so B is present in large amount as compared to A and C, while A and C are in lesser amount and are approximately equal. Area will be equal. So the main interest in any chromatographer is a good separation or resolution between the neighboring peaks. That is also required. Resolution must be very clear so that they must be separated. So this helps in accurate qualitative analysis and quantitative determination of solutes being separated from a mixture. So the resolution of chromatographic peaks related to the following two factors, that the column efficiency and separation factor, that is the solvent efficiency. So column efficiency is concerned with the peak broadening of an initially compact band as it passes through the column. The broadening results from the column design and operating conditions. This can be quantitatively described by the plate height, while which is that length of the column necessary to at, for the attainment of solute equilibrium between the moving gas phase and the stationary liquid phase. Then the separation factor, column efficiency and separation factor. So separation factor, that is alpha, on the other hand, it results from the solute solvent interaction and determines the relative position of the solute peaks on a chromatogram. The separation factor or relative retention is expressed as the ratio of retention times. Thus alpha is determined by the respective distribution constant Kc of the solutes in the liquid phase at a given temperature. So you can see this one is the normal. So the column efficiency, if you increase, then there will be better separation, more theoretical plates will be there, so better separation will be there. So in this case, increased column efficiency, still we increase greater ratio of retention time, more sharp peaks are observed. Okay, then in detail we will discuss the column efficiency. The column efficiency is measured by the plate number n. To compare column efficiency, one must specify the liquid stationary phase, solute, temperature, flow rate of carrier gas, and sample size. As stated earlier in Unit 4, I think the plate concept is a carryover. The plate concept is a carryover from distillation process, where historically the first efficient column were in fact composed of discrete plates. In the laboratory, however, packed distillation columns are more commonly employed, and the plate number is a theoretical concept. So in gas chromatography, so as the discrete plate is an artificial concept, the plate number obtained in this method varies greatly and should not be taken as a direct measure. So this figure shows the normal distributive curve. So the inflection point here at point 0.607 of the peak height. You can see here. This shows the measurement need to be made in calculation. So different terms arise. So you can see the relationship here, n equal to Tr divided by sigma whole square. which is equal to 16, that is the 16 the plate number, Tr by Wb whole square into, which is equal to 5.54 Tr by Wb whole square. So the quantity W is the width, peak width. Okay, Tr is the retention time. So base widths correspond to 4 delta as indicated. So different terms arise because measurement of a sigma can be made different heights in the peak. At the base of the peak width, half of the peak width, that is Wb, is 4 sigma. So numerical constant 4 square or 16. This is sigma square over there. At half width equal to 2.354. So square of that one. So and the constant becomes 5.54. Independent of the symbols used, both the numerator and denominator must be given in the same unit, and therefore n is unitless. So again, if you give the plate height h, then W into h equal to L by n, where L is the column length, h has the unit of length and is better than n comparing the efficiency of the column of differing lengths. It is also called height equivalent to one theoretical plate, HETP, in terms a term which is generally carried over from distillation terminology. A good column will have large plate number and small plate height or the column length. Another measurement of efficiency of a column is the resolution, that is RS. So the theoretically or by definition, it will be equal to Tr into B minus Tr into A divided by Wb of A plus Wb of B divided by 2, which is equal to 2D, and Wb of A plus Wb of B. So D is the distance between the peak maxima of two solutes A and B. This one. So this tells about the way how the resolution will be calculated. Tangents are drawn to inflection points in order to determine the width of the peaks. So like this. So you can see this one. So it is half of Wa, half Wb, width of the peak from the tangent, and from this to this the D. So Rs, therefore Rs will be equal to D by Wp. So in this figure, the tangents are touching to each other. This one. So in such case, so D will be equal to Wp. This will be equal to this. So Rs, that will be equal to 1. The larger the value of resolution, the better the separation. The better the separation, complete baseline separation requires a resolution of 1.5. So if resolution will be 1.5, then there will be complete baseline separation. Now comes to the rate theory. So it has been mentioned that there has no qualitative relationship between, there is no sorry, there has to be quantitative relationship between plate height and column variable. In this context, several chromatographic theories have been developed, out of which is one, the rate theory. So the three principal contributions to the broadening of a band are multiple path effect or eddy diffusion, A term, molecular diffusion, that is B term, and resistance to mass transfer, gas or liquid, that is C term. So these three terms, so if you compare or you accumulate, then from these the basic equation can be derived for the plate height in a gas liquid system, H equal to A plus B by U plus Cu, where A, B and C are above mentioned constant, and u is the linear velocity through the chromatographic column. It's the flow rate. Linear gas velocity is measured by length of the column upon retention time of air, so centimeter per second. So if h is plotted against u, one obtain a hyperbola. This one with minimum h, this minimum is the this minimum is that flow rate, that is u will be optimum. That's this one, the minimum of h at which the column is operating most efficiently. So the expanded version of this Van Demter equation, the theory which was developed by Demter. So the developed equation is this one, HETP, which is equal to, that is the equivalent to one theoretical plate. HETP is equal to 2 lambda dp plus 2 nu d of gas upon u plus 8 k prime d square f divided by pi square 1 plus k prime whole square d of liquid into u. So where lambda is a parameter which is a measure of packing irregularities, dp is the diameter of packing particles, gamma a correction factor accounting for the uh, tortuosity of the gas channels of the column, dF is the effective film thickness, a measure of liquid loading of packing material. D liquid is the diffusion coefficient of the solute in the liquid phase. D gas is the diffusivity of the solute in the gaseous phase. U is the linear gas velocity, and K prime is the capacity factor, where this F of liquid to F of gas. Now, the conclusion which have been drawn from the rate theory, that one is the particle diameter. So the column efficiency is improved by the use of small and uniform particle size. Supports which give the highest efficiency are diatomaceous earth type with 100 to 120 mesh range. Now flow rate, for maximum efficiency the column must be operated at the optimum flow rate. This is found by the plot of h against the flow rate. The minimum h determines the optimum linear gas velocity or the flow rate to be used. As in this case, so this is the minimum optimum flow rate, 0.2 centimeter per second nearly. So in practice, operating at flow rates slightly higher than optimum will decrease the analysis time and not materially affect the H. Then the carrier gas. The detector employed usually detect the choice of the carrier gas. However, for the high efficiency, a high molecular weight gas should be the choice, where rapid analysis time is required and the high efficiency is not necessary. A low molecular weight carrier gas must be chosen, such as helium or hydrogen will be preferred. The type of the liquid phase, a low viscosity, low vapor pressure solvent with good absolute solubility for the same should be used. For the sample should be used. To obtain a separation, it must also exhibit a differential solubility, an amount of liquid phase, low liquid loadings, it means a thin film of 1% to 10% have the advantage of fast analysis and lower temperature operation. Low liquid loadings, however, reduce the sample capacity and may require highly inactive solid supports. In pressure, a majority of Practical gas chromatographers work at an outlet pressure of 1 atmosphere so that operation at optimum flow rate fixes the inlet pressure. The temperature, so lowering the temperature also decreases the decomposition of the compound, but it may increase the adsorption. So simultaneous reduction of liquid loading and temperature is generally beneficial. The limit to this is the increased exposure of active sites of the solid support and the need for sensitive detector. And column diameter, capillary and preparative column experiments indicates that efficiency is improved with decreasing internal diameter. Then with column efficiency, we move next to the solvent efficiency. So it is a striking picture that gas chromatography is that substance having the same vapor pressure can be easily separated by appropriate selection of the liquid phase. The major advantage of gas chromatography over distillation is the ability to use selective solvents. There are numerous selective phases available, and the following factors should be considered for the selection of a proper one. Interaction forces and partition coefficient. So there are four interaction forces which can aid the GC separation. Kisum type of forces, that is orientation or Kisum forces, forces which resulting from interaction between two permanent dipole. The hydrogen bond is a particularly important type orientation. So we have Kisum forces, Debye forces, then London forces. Okay, as the intermolecular force of attraction, already we have known these things: dipole dipole interaction, ion dipole interaction, induced dipole interaction. So basing upon this, these are the forces. Orientation or Kisum force, it is the dipole dipole interaction between two permanent dipoles. One example is the hydrogen bonding. Then the induced dipole interaction, that is the Debye force. The force resulting from the interaction between a permanent dipole in one molecule and the induced dipole in a neighboring molecule. This force is usually very small. Then the dispersion, that is London or non-polar forces. Forces arising from synchronized variation in the instantaneous dipole of the two interacting species. These forces are present in all cases and are the only source of attraction energy between two non-polar substances. They are weak compared to A and B. Then specific interaction forces, forces resulting from chemical bonding, complex formation between two solutes, between solute and solvent. These forces of interaction determines the solubility and thereby the separation is achieved. Their combined effect are expressed by the distribution constant Kc, where Kc is the amount of solute per unit volume of liquid phase upon amount of solute per unit volume of gaseous phase. So the value of Kc is high when most of the solute is retained in the liquid phase. This means that the solute moves slowly down the column because only a small fraction will be in the carrier gas at any given time. So then the solvent efficiency and temperature. Solvent efficiency is measured by alpha, the relative retention. It is the ratio of adjusted retention time or partition coefficients. The calculation of solvent efficiency is illustrated in this figure. So adjusted retention time and the volume uncorrected, this is the corrected one. So solvent efficiency will be equal to x2 prime upon x1 prime is k2 upon k1. So separation factor, that will be equal to x2 by x1, x2 by x1, and this is the adjusted one for air. So x2 prime, this is x1 prime. So x2 prime by x1 prime. So the relative retention differs from the separation factor, where separation factor is the ratio of uncorrected retention time. So both alpha and Kc are temperature dependent. However, over a limited temperature range, alpha will be a constant. The distribution constant decreases with increasing temperature. That is, the fraction of solute in gaseous phase will increase, and hence the elution time will decrease. So this results in decrease in separation since it is the liquid phase which performs the separation. No separation occurs in the gaseous phase. The number of plates for required separation. So the equation that already you know, the number required equal to 16 r square rs square alpha by alpha minus 1 whole square k2 plus 1 by k2 whole square, where k2 is the capacity factor for peak 2. So this is adjusted retention time upon retention time for air. So RS is the resolution required and alpha is the solvent efficiency. Both we have already defined. So the number of plates required can be illustrated in this following example. So one example is given, you can see there. So separation you can see here is obtained with a 3-meter column. What is the minimum column length necessary to obtain a resolution of 1.5? So retention time is given for two samples, one is 17 minutes and 14 minutes, and this is 1 minute is given for the solvent. So n original, that is equal to 16 x by y square minus, so which is equal to 16 into x is 17, y is this one 17 by 1, so 4624 plates are required. So alpha will be equal to 17 minus 1 divided by 14 minus 1, will be this 2, 1.231, and k2 equal to 17 minus 1 divided by 1, so equal to 16. So if you put all these values in this equation, so finally it is giving required plate 1155. So it was 4624. So like this you can show L required, that will be equal to L original into number of plates required divided by original. So 3 times, so 3 into this one. So length of the column should be 0.75 meter. So thus a much shorter column will provide a satisfactory separation. Since the separation is complete on the 3-meter column, so higher flow rate can be used to reduce the analysis time. Now move to the instrumentation. So as shown in the figure, schematically we have shown the instrumentation. We have the carrier gas cylinder, then flow meter, then sample injection chamber, then the column, then oven, detector, electronics recorder, and fraction collector. So these are the different parts of the instrumentation process. Here the mobile phase is that is the carrier gas. The carrier gas is normally available in a compressed gas cylinder. It is used to transport the vaporized solutes from the injection port through the column to the detector. The carrier gas, it must be inert, it must be dry and virtually free from impurities. Okay, impurities such as hydrocarbon, oxygen, as well as water, they can usually will contribute to unwanted noise levels. So the gas should be free from all these impurities. Therefore, additional peaks are also seen in the chromatography. You can see here some other peaks are also there. Effect of water on column efficiency. So therefore, the gas should be pure. Generally, the detector, the thermal conductivity, flame ionization, electron capture, and carrier gas may be helium or mixture of helium or nitrogen, very dry nitrogen or argon, or contain 35 sorry 5% methane we can take. The solutes of interest in the sample may also be dictate the choice of a particular carrier gas. For example, in the analysis of hydrogen in air, nitrogen should be the best choice. Then the flow controller and pressure regulator. The measurement and control of carrier gas flow is essential for both column efficiency and for qualitative analysis. So therefore, the stability is necessary for accurate results, reproducibility for precision, and convenient parameter adjustment to optimum results. For this reason, a specially designed flow controller or pressure controller is used to maintain precise and accurate flow rates for column carrier gas or for auxiliary gas needed for detection operation. Then we move to the column, which is the most important part of gas chromatogram. Gas chromatograph. It may be called as the heart of the instrument. Most columns are usually constructed of gas or metal tubing filled with a carefully sized granular solid support. The grains of the support are typically coated with a relatively high boiling liquid phase. This liquid phase, often referred as the stationary phase, is the active portion of the column. It is the interaction of sample solutes with the liquid phase that determines how much separation can be achieved. Some columns do not use a liquid phase but rather employ porous polymers or solid absorbents to achieve separation. Each type of column describes how its own grouping of application. So the column, the packed column. Another type of column is the open tubular column, which is usually 0.25 millimeter internal diameter tubing. A liquid phase is coated directly on the inside wall of the tubing. Okay, therefore no additional packing is needed due to small surface area involved and the resulting limited capacity for solutes. These columns are necessarily long, 20 to 50 meter, and require the use of specialized sample inlet. Since capillary columns are not filled with particles, band broadening due to eddy diffusion does not exist. The design of an open tubular column is shown here. Okay, so all the columns, the components are separated. Then the stationary phase, support, and liquid phases. So stationary phase support. The purpose of solid phase is to support a thin uniform film of liquid phase, and optimum support should have these characteristics: a large specific surface area from 1 to 20 square meter per gram, a pore structure with uniform pore diameter in the range of 10 micron or less, inertness, that is a minimum of chemical and absorptive interaction with the solutes. Regularly shaped particles must be uniform in size for efficient packing, and mechanical strength. It should not crush on handling. So this must be the criteria to support or to select the column. So in that case, the raw material for most gas chromatographic support is diatomic diatomite, also known as diatomaceous silica, diatomaceous earth, or Kisselgore. So these are the clay or silica which is filled inside the column. Then the more uniform the packing, the smaller the AD diffusion and more the column efficiency. For 3 millimeter internal diameter column, 100 upon 120 or 80 by 100 mesh support is preferred. For 6 millimeter internal diameter column, 40 by 60 or 60 by 80 mesh is suitable. That means the particle size. Then the chemical analysis for supports. The chemical composition of some columns or supports is given here. Then the liquid phase. There is no foolproof method for selecting the best liquid phase for a particular separation. The right selection is based mainly on experience. So, some requirements of liquid phase: it should be a good absolute solvent for sample solutes. If solutes are sparingly soluble in the liquid phase, they will be eluted rapidly and separation will be poor. So next one, it should exhibit differences in solubility for different solutes in the sample. It should have low vapor pressure at operating temperatures for a reasonable column life. It should be thermally stable. It should be chemically inert towards solute of interest at the column temperature. So these are the recommended liquid phases by sample type. It is the stationary phase. What is the classification of compounds? So you can see here. All these things are given. You can go through that one. The super selective liquid phases. Super selective, why? Some of these liquids depends on the formation of loose chemical adduct with particular solute to effect separation. Like for example, silver forms loose adduct with olefins of the type shown in the figure with Ag plus. So saturated solution of silver nitrate in ethylene glycol or glycerol and triethyl glycol or in benzyl cyanide have been used as selective solvent for olefins. Okay, so as it make a bind and separation will be better. So paraffin are not retained and pass rapidly through the column while alkynes react to form silver stellite and remain on the column. Temperature should be below 40 degrees Celsius. Above this limit, the adduct with silver nitrate are not formed and solutes are solutions are unstable. Okay. Similarly, the liquid crystals are also used as selective phases. Liquid crystals are intermediate between the crystalline solid and normal isotropic liquids. They can exist in liquid crystal phase, smectic and nematic. The solid phases form smectic liquid phase to the nematic and finally to the normal liquid phase as temperature is raised. A typical formula For a liquid crystal is this one. So where R maybe CH3, okay, or it will be C6H13 alkyl group, or normal C17H15. It may be hexyl or heptyl group will be there here. Methyl, hexyl, R is CH not CH2, alkyl group, maybe N hexyl or N heptyl. The liquid crystals show a selective affinity for linear molecules. They will retain para disubstituted benzene relative to ortho or meta isomer. In the liquid phase percentage, the amount of liquid phase used should be just enough to coat particles with a uniform layer. So the change of retention time with percent liquid floating is illustrated here. You can see with 30% liquid phase at 50 degrees Celsius. So retention time will like this. 20%, 10% will just decrease, and 5% you can see the separation is also very narrow. In 10% is very difficult to separate. Retention time decreases with percentage liquid phase, decrease in percentage liquid phase. In the column temperature, it is very important factor because the distribution constant K prime Kc depends upon temperature. In most of cases, an increase in 30 degrees Celsius will halve the Kc and thus double the rate of solute migration. So the most immediate effect of temperature increase is a decrease in analysis time. So if you increase the temperature, analysis time decreases. Porapac. Porapac is a porous polymer composed of ethyl vinyl benzene cross-linked with divinyl benzene to form a uniform structure of a discrete pore size. Porapac column contain only the porous polymer beds screened to a definite mesh range, and no liquid phase or solid support is used. The porous polymer bed serves the function of both liquid phase and solid support. So this can be used. Then we'll move the detector. Once the sample is injected and separated, it should be detected. Method of detection is required. The selection of a detector will depend upon the sample, which sample we are using. So some characteristics of usefulness of detector there is adequate selectivity, sensitivity and detectability, a linear response to solutes that extends over several orders of magnitude, operative in a temperature range from room temperature to at least 400 Celsius, high reliability and easy to use, a short response time that is independent of flow use, similarly independent of flow rate, similarity in response towards all solutes, non-destructive for solutes, noise and minimum detectable quality should be there. So different detectors are there. You can see, so the thing, the internal diagram. So detector sensitivity or detectability is defined as the ratio of the smallest detectable quantity measured at twice the noise level to the peak width at base in seconds. So similarly, detector response of a detector with the quantity of a signal generated by a given amount of solute. So noise and minimum detectable quantity. Detector sensitivity can be made as large as desired when the electrical output of the detector is increased to almost any desired value by electronic amplification. However, electrical noise inherent in the detector and electronics is also amplified, and a point is reached where the noise level is high enough to obscure the detector's response. Therefore, the noise level limits the concentration or the minimum detected or mass flow rate of the solute that can be detected. So the noise should be minimum. Then the linear detector range. What are the different types of keeping in mind? Some of the detectors are that are being briefly discussed here: thermal conductivity detector, flame ionization detector, electron capture detector, helium ionization detector, and flame emission detectors. So these are the different types of detectors. Thermal conductivity detector, that is catharometer. So this is the thermal conductivity cell one detector. Then the flame ionization detector, electron capture detector. The characteristics of electron capture detector: specific, selective to halogens, sensitive to a few parts per trillion. It should be highly sensitive. And helium ionization detector, flame emission detector, that is alkali flame detector. The schematic diagram. Then the sampling part, sampling and introduction of sample into the gas chromatograph unit. So the sampling process involves the steps: removal of an aliquot from a bulk quantity which is representative of that bulk. If necessary, alteration of the physical state of the sample, that of gas, so that it can be manipulated. Transportation to the laboratory for analysis, storage prior to analysis, then introduction of the sample into a GC unit for analysis. Hazards in sampling, so hazardous chemicals should be handled carefully. Then introduction of the sample to the GC unit, it depends upon the sample's size, injection system, and sample injection port. So the sample volume may vary depending upon the amount and rate of evaporation of the sample in the sample port. In case of liquid or solution of the solid, or on the pressure of the gas or vapor, sample contained in a sample container. In the case of gases, it is a common practice to vary the amount of sample by introducing different volumes at constant pressure. The injection system: various kinds of injection systems have been incorporated. So that is a direct injection, split injection, and splitless injection, solid injection or moving needles there, on column injection, valve injection, thermal disruption, cold trap injection, purge and trap injection. So these are the injection systems. So one is the sampling syringe through which it can be injected. Simplified injection port, you see here, for one column injection. In the gas sampling valve. So small now the application is used for identification of compounds, quantitative analysis. So in quality, both used for qualitative and quantitative analysis. Some example, if you see, then the bacterial identification. In environmental analysis, you use what for water analysis, air analysis, clinical and toxicological analysis, forensic toxicology. So these are the applications of gas chromatography. So in summary, and some questions are there. Okay, so this ends your uh, unit 7. We'll start unit 8, that is high performance liquid chromatography, HPLC. Just we'll have a 5 minute short break, then we'll come. Okay, we'll start the next unit, that is SVLC, or the high performance liquid chromatography. The course structure is like this: introduction, principle, instrumentation, then optimization of separation, advantages, comparison with gas chromatography, then application. This is high pressure liquid chromatography or high performance liquid chromatography. To distinguish from old procedure, modern HPLC has emerged from the confluence of need, the human desire to minimize work, technological capability, and the theory to guide development along rational lines. So the basic principle of separation by high performance liquid chromatography is similar to classical liquid or column chromatography, though it differs with regard to the size of the column and the sample. It differs from liquid chromatography in terms of speed, automation, illusion time, and individual manual assays of collected fractions. In case of SPLC, microgram amounts of sample is allowed to pass through a column containing stationary solid inert phase coated with non-volatile liquid phase by means of a pressurized flow of a liquid mobile phase where components migrate at different rates due to different relative affinities. Comparison to column chromatography. Comparison of column size, characteristics of packing material, and pressure required to force the mobility of mobile phase. In classical column chromatography and HPLC are illustrated in this figure. Okay, the classical chromatography, B is the HPLC, and C HPLC with microparticulate packaging. So column size you can compare. So according to the another version of SPLC, another version SPLC may be considered as partition chromatography, where stationary phase is a second liquid coated on an inert surface and it is miscible with the liquid mobile phase. According to the stationary liquid phase, the technique may be subdivided into two types: liquid liquid and liquid bonded phase chromatography. These differ from each other in the way stationary phase is held on to the support. In liquid liquid chromatography, the polar liquid is physically adsorbed onto an inert surface where it competes with the mobile phase. However, in case of bonded phase chromatography, liquid is chemically bonded, making a more stable, making it more stable. So, okay, in order to achieve the desired separation by HPLC, several operating conditions, including retention time, pressure, and number of plates, need to be optimized, as in case of earlier we have already discussed. A major interest in short analysis time or the plate count needed to accomplish a difficult separation. First of all, a proper HPLC system such as adsorption, bonded phase, reverse phase, ion exchange, exclusion, affinity, or any other form of chromatography must be selected. So these equations that we have discussed, and remember all these things. So logarithmic plot of reduced plate height against reduced velocity. Then we move the instrumentation. The instrumentation of general SPLC have the following components: one or more solvent reservoirs for the mobile phase. Let's see here. A pump to deliver the mobile phase with varying range of pressure up to several hundred atmospheres to achieve reasonable flow rate. Sampling valves or loops where the sample may be injected into the flowing mobile phase. Sample may be dissolved in mobile phase. A guard column or an online filter to prevent contamination of the main column. So we must have a guard column. Then a pressure gauge inserted in front of the separating column to measure the column inlet pressure. Separation column containing packing to accomplish desired separation. These may be modified silica gel or ion exchange resin or gel or some other unique packing. A detector capable enough to of measuring the solvent concentrations. Display and recording device for plotting time versus peak intensity. Other electronic accessories for data manipulation are also required. So this is shown in this figure. Then we'll move to the sample injection system. This is the schematic diagram of injector valve with external sample loop in a micro volume sample. It is a limiting factor in the precision of HPLC measurement because of reproducibility with which samples may be introduced into the column packing. Insertion of the sample into the column must be through a narrow plug so that peak broadening is minimized and the system should have no dead volume by itself. Generally, samples are dissolved in a mobile phase solvent to avoid solvent peak, and 10 to 50 microliter is introduced through sampling valves. These devices form an integral part of the liquid chromatography equipment, having interchangeable loops with a choice of sample size from 5 to 500 microliter. The most widely used method of injection is based on sampling loop as shown in the figure. It is filled by thoroughly flushing it using a sample solution by means of a micro syringe at a pressure up to 7,000 Pascal per square inch. So in the column, which is heart of the HPLC instrument, where the actual separation occurs. Separation column in HPLC is usually made of heavy wall glass lined metal or 360 grade stainless steel tubing that can withstand high pressure and which is inert to the chemical corrosion due to the mobile phase. The interior of the tubing must be smooth with a uniform bore diameter. Stainless columns that can be operated in vertical position are preferred. Some typical tubing are also given in the table. What are the material? What is the use of the tubing? If it is stainless steel, General utility material good for high pressure system, polyether ether ketones, Tefzel, titanium, fused silica glass, glass or glass-lined stainless steel. These are the different materials which are used for preparation of column. Column fittings and connectors must be so designed that void volume is zero, avoiding unswept corners. Column length range from 10 to 30 centimeter with inner diameter 2 to 5 millimeter, providing for 40,000 to 60,000 plates per inch is the adequate one. However, shorter columns of 3 to 8 centimeter also are there. Then in column we have the guard column. So in order to increase the life of analytical column, a short guard column is known as also pre-column. Is placed before the main column, already shown in the instrumentation. It removes contamination from the solvent. Guard column serves to saturate the mobile phase with the stationary phase so that losses of stationary phase in the column are minimized. However, it is essential that composition of the guard column should be similar to that of analytical column, but its particle size may not be larger to minimize the pressure drop. Then the packing material or the stationary phase. The packing used in modern HPLC consists of small rigid particles with a narrow particle size distribution. The most common packing materials used for LC liquid chromatography is prepared from silica, it may be acidic, or alumina, which is basic. Silica or alumina particles, which are synthesized by agglomerating submicron size particles under conditions that lead to larger particle diameter. These are often coated with thin organic films which are physically or chemically bonded to the surface. For nearly all HPLC applications, chemically modified or unmodified microparticulates silicas of 3, 5 or 10 micrometer diameter are preferred. So there are the characteristics of some commercial HPLC column packing materials. Silica and alumina we have used. Various shapes of stationary phase packing with HPLC: bonded, that is spherical phase; irregular, large porous phase; pellicular particles, beads, and porous microparticles. The pores are there. So what is the spherical bonded phase? These spherical packings consist of a solid spherical non-porous core, usually a glass bead, with a layer of attached functional groups forming an outer shell containing unmodified or modified silica gel, resin, or polyamide, etc. Various functional groups are used depending on the nature of solutes to be separated. In the porous layer beds, a porous or pellicular layer bed type packing material consisting of a solid spherical with an average particle diameter of 30 to 40 micrometer, coated with a thin porous outer shell, typically of 1 to 3 micrometer thick. It may be a silica gel layer, a network of small spherical particles bonded to the solid core. It may also be monomeric or polymeric organic phase. Surface areas of the porous layer bed range from 5 to 15 meter square per gram. So, in the porous particles, totally porous particles have large surface area in the range 100 to 860 meter square per gram, with average being 400 meter square per gram. The mean pore diameter is inversely related to the specific surface area where small molecules enter the pores. The particles can be packed into the HPLC column of efficiencies up to 800 theoretical plates per centimeter if 5 micrometer particle size are used. However, larger particles give proportionately small number of theoretical plates, hence the efficiency of separation goes down. Then the macroporous particles, these are recently introduced graphitized carbon and styrene divinyl benzene polymers having large channels besides micropores. The rigid porous polymeric microporous beads do not swell or shrink with change in the ionic strength of the mobile phase, so it can be used over an extended pH range from 1 to 13. They don't deform at high velocities and are most suited for separation in non-aqueous media. These materials have increased the choice of stationary phase and the scope of HPLC. So various types of bonded phase used in HPLC are given here, shown here. So therefore, now let us study about the stationary phases used in various chromatographic methods. What are the different stationary phases? As the adsorption chromatography, in majority of these cases of adsorption chromatography, silica is the common packaging material and are used when where main mechanism is the interaction of its hydroxyl groups with the polar or unsaturated functional groups of a solute or solvent molecules by hydrogen bonding or dipole-dipole interaction. The slightly acidic silanol, that is silicon hydroxyl group in silica gel, are at the surface and extends out from the surface in the internal channels of the pore structure. The number and topographical arrangement of the several types of OH groups is given in the figure. Structure of silica gel depicting the various types of hydroxyl group that interact with the functional groups of solute solvent molecules. So the hydroxyl groups can be divided into three types, that is silanol, that is free hydroxyl group, siloxane bond, that is silicon oxygen silicon bond, and hydrogen bond with silicon hydroxyl group and oxygen. Silicon hydroxyl group and oxygen, silicon oxygen silicon bond, that is siloxane bond. Here the hydrogen bond and isolated hydroxyl groups. There is no bonded hydroxyl; these are isolated. Okay, so according to current model, or each of these groups have different activity that increases in the following order. Bound is less than free and less than hydrogen bonded. So according to the current models of adsorption process, it is assumed that adsorption sites are completely covered by either of solute or solvent molecules that are adsorbed depending on their relative strength in this competitive interaction. The competition between the solutes and the mobile phase molecules for an active site provides the driving force and selectivity in separation. So adsorption chromatography is less influenced by difference in molecular weight but certainly more by functional groups. For compounds of low to moderate polarity, adsorption chromatography often makes possible the separation of complex mixtures into classes of compounds with similar chemical functionality. Then this is on adsorption chromatography. Then on partition chromatography, which is again divided into liquid-liquid chromatography and bonded phase chromatography. The difference being in the method by which the stationary phase is held on the support particles of the packing. In case of liquid chromatography, a liquid stationary phase is retained on the surface of the packing by physical adsorption, where with bonded phase chromatography, the stationary phase is adsorbed, is bonded chemically to the surface of inert support. So here you can see silicon and this chlorine. The surface of fully hydrolyzed silica is made up of chemically silanol groups. The most useful bonded phase coating are siloxanes formed by the reaction of hydrolyzed surface with an organochlorosilane as shown in this figure. So surface coverage by silanization is limited to 4 micromole per meter square or less because of steric effect. The unreacted silicon hydroxyl groups impart an undesirable polarity to the surface which may lead to chromatographic tailing of the peaks. In order to avoid this effect, siloxane packing are often capped by further reaction with chloromethylsilane that can react with many of the unreacted silanol groups. So two types of partition chromatography has been recognized based on the relative polarities of stationary phase and mobile phase. In normal liquid chromatography or HPLC, stationary phase consists of high polar water or triethylene glycol supported on silica or alumina. So perhaps quarters of all HPLC is currently being carried out in columns with reversed phase. So the most commonly alkyl group of the siloxane in these coatings is N-octyl, already discussed, containing 8 carbon atoms, or N-octadecyl containing 18 carbon atoms. So what is the column packing and mobile phase? The table is given here. Relationship between the polarity of the sample with that of the packing material and the mobile phase in reverse phase HPLC. Then the ion exchange chromatography. In this case, column packing have charge bearing functional groups attached to the polymeric matrix. The functional groups are permanently bonded ionic groups associated with counterions of the opposite charge. Some ion exchange packing bear negatively charged groups and are used for exchanging cationic species, whereas others are designed for exchanging anionic species. Similarly, some functional groups such as carboxyl or phosphide have weak acidic or basic properties, whereas some other have considerable affinity for heavy metal cations. So these are shown in this figure: ion exchange film, inert core, anion resin beads, micropores. Okay, then anion exchanger, surface sulfonated and bonded electrostatically. So during preparation of ion exchanger by silylation, a vinyl group is chosen for R3 in SiO, SiR1, R2, R3